Section 9.2, physical properties of alcohols. And I'll just forewarn you that with this section, it's going to be something you should probably go ahead and read a couple of times in the textbook, just to make sure you understand the concept of hydrogen bonding properly, and that you understand polar, nonpolar regions of an alcohol, and that you understand that the polar region, the hydroxy group, is going to be water loving or hydrophilic, and the alkyl portion is going to be hydrophobic or water hating. All right, so what happens when you try to dissolve an alcohol in water? Well, you know that ethanol, which is the alcohol found in alcoholic beverages, is soluble in water. And ethanol is what we would consider to be a low molecular weight alcohol, right? It only has two carbons, six hydrogens, and one oxygen. So this is ethanol. So again, ethanol, it turns out, is soluble in water in all proportions, just like methanol, propanol, and butanol. But once you get to five carbons, you can see here that the alcohols start to have limited solubility in water, right? So it's presumed that if we were to extrapolate this line up, right, any lower chain alkane, so anything with less than five carbons is going to be soluble in water. But once we get to five carbons, you can see the solubility is decreasing, right? It's going down and down and down from one carbon or five carbons in pentanol to six carbons in hexanol to seven carbons in heptanol. The water solubility is decreasing. And the reason why that happens is because an alcohol has two portions, doesn't it, right? I'm going to draw the structure of methanol here. So this would be methanol, which is completely soluble in water. And let's compare it to pentanol, one pentanol, as a matter of fact. That is much less soluble in water. You can see the pentanol is right here, okay? And methanol is not shown on the screen because it's completely soluble. So I'm just gonna remove that line for now. Anyhow, if we look at the structure of both of these, right? You see that both of them have a hydroxy group. Now that hydroxy group is going to enhance the solubility of the alcohol in water to some degree. So this is going to be water loving or hydrophilic. Okay, so we'll just put here water loving. Okay, water loving. Again, you should know the proper term, hydrophilic, right? However, we also have this alkyl portion over here, and we have the alkyl portion here in methanol and pentanol, respectively. Now, the alkyl portion is made out of only nonpolar bonds, carbon-carbon bonds, and carbon-hydrogen bonds. And so it is going to be water hating or hydrophobic. So I'm kind of mixing the two things here, but I'm just going to put hydrophobic, right? Here, hydrophobic. Well, what do you see? Well, what's the difference between the two of these? The hydrophobic portion in methanol is much smaller than that in pentanol, and therefore the hydroxy group is going to have a much stronger effect in methanol. Okay, again, this is my methanol, than it would in my one pentanol, right? The hydroxy group is there in one pentanol, but the hydrophobic portion is so huge that it limits the solubility of the alcohol in water. And you can see what the trend is. As the chain gets longer and longer, as we go from six to seven to eight to nine to 10 carbons, then we get to a point where the alcohols are completely insoluble in water. Now, just to kind of uh, add some more detail to this, it says here low molecular weight alcohols are highly soluble in water. Why? Because hydrogen bonding between the alcohol and water molecules is more meaningful or stronger, or yeah, meaningful might be a better word than stronger. It's the same force, but more meaningful than the London dispersion forces present in the limited amount of hydrocarbon. Right. So if we zoom in here, this is showing hydrogen bonding between. This is a molecule of oops, look at my highlighter. This is a molecule of methanol here, and this is a nope. This is a molecule of methanol here. This is a molecule of methanol here, and I'll highlight this is a molecule of water, and this is a molecule of water. But you see those dashed lines that represent the hydrogen bonds, and you see that the nonpolar portion is very small, okay, with methanol. But if we take a look at this example that they showed here, which has one, two, three, four, five, six, seven. So this is one heptanol. This compound here. So this is one heptanol, okay? And then this is a water molecule here, and this is a water molecule here. So in this case, it says here that, again, the reverse is true for high molecular weight alcohols. So water interacts with only the hydroxyl group of one heptanol, which is insufficient to make it soluble in water because it has such a gigantic hydrophobic portion, okay, that long chain. So again, the longer the chain is, the more the effect of insolubility is exacerbated. All right, now how does hydrogen bonding affect the boiling point of alcohols? Well, hydrogen bonding causes alcohols to have higher boiling points than most other compounds of similar molecular weight, as it takes more heat energy to break apart the hydrogen bonds compared to weaker intermolecular forces, such as dipoles, okay, or London dispersion forces. So ethanol, it turns out, ethanol, which is the alcohol again, that's found in alcoholic beverages. It boils at 78 degrees Celsius, whereas dimethyl ether, so dimethyl ether is this compound here, CH3OCH3, which has the exact same molecular formula, right? They are both C2H6O, but it boils at -24, meaning it's a gas at room temperature. Why? Because it doesn't have hydrogen bonding in it, because even though there's an oxygen in it, the oxygen is not attached to a hydrogen, is it? It's attached to two carbons. And then we have propane, which has a molar mass that's almost identical to that of ethanol and dimethyl ether. It's very close. It's within like 1 or 2 mass units. And it boils at -42, okay, extremely cold. And again, the reason why is because the propane, all it has are London dispersion forces. If we go to the dimethyl ether, it has London dispersion forces, of course, and it also has dipole forces. But then when we get to the ethanol, right, here's a molecule of ethanol shown right here, okay? It has hydrogen bonding, which is the strongest of the intermolecular forces. It has dipole-dipole interactions, and it also has London dispersion forces, right? It has all three. So consider these compounds, and it says here, arrange these compounds in order of increasing solubility. So increasing solubility. Well, the first one is 1 propanol, propanol, okay? You could also call it propyl alcohol, right? Because we know what a propyl group is, so propyl alcohol is totally fine. The next one is an alkane. This is propane. I'll just write way up top here. And the last one, I showed you this earlier on. This is ethylene glycol. Ethylene glycol, which is a common name. The systematic name would be 1,2-ethane diol, but I can't imagine why anybody would call it that. Okay. Well, when it comes to increasing solubility in water, you can see that ethylene glycol is going to be the most soluble in H2O. Why? Because it has two hydroxyl groups, which can participate in hydrogen bonding with water. And you can see that the propane is going to be the least soluble because it has no hydroxyl groups, and then the propanol is going to be somewhere in between because it has one hydroxyl group. All right, next it says arrange the compounds in order of increasing boiling point, i.e. lowest boiling point first, highest boiling point last. Well, the lowest boiling point of all of these, so I'll put down here lowest boiling point, we'll just put BP, is going to be the propane. Right, it has no hydroxy group to participate in hydrogen bonding. That's going to be followed by the one, the 1 propanol, which has hydrogen bonding, but it's not going to be as much as the ethylene glycol, is it? Right, because it's got two hydroxyl groups for hydrogen bonding, so it's going to have the highest boiling point of all. And that's why we put ethylene glycol in a car's radiator. That's why it's found in, Prestone, okay, automobile antifreeze, because even if the engine gets hot, um, ethylene glycol is a very high boiling point, okay, so it won't cause your engine to break down, okay. It also decreases the freezing point of water, and that's why it prevents your radiator from cracking in cold weather.